Hello, everyone. So I have pleasure to introduce Dr. Billy Lee, and he'll be talking about world's first undoable notebook. So let's give it up for Dr. Lee.
All right, hi everybody. My name is Billy. Just a side note, I'm not a doctor yet, but hopefully I'll be one soon. But anyways, today I'm here to present my work, Kishu World's First Undoable Notebook. So before we start, can I see a show of hands of like how many of you use notebooks for work? All right, great. So when using notebooks, how many of you have run into like problems, say like you ran a cell and then immediately regretted doing that? For example, if your cell like dropped the data frame column, or if you overwrote some data that you assigned to like a very generic variable name, or if you ran some in-place updates which turned out to be less than ideal. Have you any of you experienced that? All right, great. I'm also one of you. So because of this, I'm going to be talking about a notebook checkpointing system that we made. It's called Kishu, which allows users to roll back cell executions along with some other very helpful features. So you can see here the user ran a cell that dropped the data frame column, but then it's fine because they can just click undo with their system and then they'll get that column back. And to begin, I want to do a bit of a brush up for the folks who are probably less familiar with notebooks. And the way that notebooks work is that versus say like just conventional Python programs, they contain this so-called session state, which tracks intermediate execution results. So for example, if the user runs a cell that declares two variables, the notebook session state will remember that, along with a bunch of other metadata that I'm not going to go into too much detail about. And because of the session state, notebooks are actually very effective at enabling iterative programming, where users can write programs incrementally, and this is very useful for tasks involving a lot of trial and error. For example, for me, when I was an undergrad and taking Baby's first artificial intelligence course and just running random cell code and hoping something sticks. So my workflow would probably look something like this, where I start with, like, say, importing some libraries, running some more cell code to load and check the data, run some cell code for data cleaning, do some feature engineering, and then, whoops, that didn't work, but then it's fine because I can always just edit the cell code and try again, and then hopefully proceed to train some ML models. And one issue that can arise in the middle of all of this is that the notebook session state can actually be lost. And it can happen because a notebook session state is stored entirely in memory, which means it's non-persistent. So if your session crashes for whatever reason, you will lose it. So suppose I was training my ML model from earlier, and one of these things happens. For example, my kernel crashed because I ran out of memory. Or if I realize I need to actually terminate the current session and switch to a machine with more powerful resources. Or my personal favorite, when I'm working on an assignment with a deadline that's like up and coming, and I walk away to grab a cup of coffee, and when I come back, my Colab session has just disconnected, which is very unfortunate. So if either of these things happened, the cell code and the cell outputs are still going to be there, but then all of the variables that are contained in my session state will be gone. So I cannot actually resume working on my task immediately from where I left off, which may or may not lead to some more severe consequences depending on what I'm working on. And because of similar reasons, a notebook session state also does not record past states. And what that means is that if users run a cell that does something irreversible, like dropping data frame columns, which is, by the way, very common in platforms like Kaggle, because notebook sessions on those platforms have like very, very limited memory space. So if the user does something like this, and then later on, when they might realize that they actually needed those data frame columns, then they actually cannot undo that cell execution to undrop the data frame columns. And another thing that many users do is to copy and paste cell code. For example, given this code snippet here, they might copy it, paste it into somewhere else in the notebook, make some minor modifications, and execute it. And then by doing that, they've just overwrote a bunch of variables. And because of similar reasons, current notebooks don't support unoverwriting variables. And it turns out that the notebook users are aware of this problem of like session state loss. People have asked on forums like Stack Overflow and Colab forums about whether they can restore the data after runtime disconnects. And the answer to this question is unfortunately no as of now. And people have resorted to some like very innovative and funny methods to prevent their Colab sessions from disconnecting. And similarly, people have asked about whether they can undo commands in Jupyter Notebook after executing a command, and the answer to that question is also similarly no. So based on this, I want to introduce some methods that are common for users to actually perform for restoring on their session state. The most straightforward one is just to rerun all the cells. So it turns out in notebook systems like Google Colab, Jupyter Lab, or Kaggle, there's this very convenient button called rerun all, which just basically executes all of your cells sequentially, which may or may not work. So there are two downsides to this. One is that depending on what you have in your notebook, rerunning all the cells may take a while. For example, if you're rerunning a cell to retrain an ML model, that might not be ideal. And another more important problem is that the current cells that you have in a notebook might not be the same as your previous execution history. So rerunning all the cells sequentially might not actually get your session state back before your kernel crashed. So instead of rerunning cells, some users have also experimented with just dumping the entire state using some tool like, for example, Pickle or Dill. So Dill has this very convenient function called dump session. I think it was renamed to dump modulator, which basically serializes your entire session state to disk into a Pickle file, which if your kernel does crash, you can load that Pickle file to get all of your variables back. And researchers have actually built tools upon, say, dump session. This is a paper called ForKit, where researchers have proposed that you can basically just dump the entire session state after every cell execution. So, for example, the user might run a first cell where they import packages. They would dump the state, run some more cells to import the data set, and then after every single cell execution, you end up with more and more Pickle files. And there's a very obvious problem with this approach, being that because you're dumping the entire state after every single cell execution, even though the data set size you're working on could be, say, modest, you can often just end up with, say, gigabytes of checkpoint files on disk, which is not ideal. So as an alternative to state dumping, researchers have also experimented with just applying OS-level checkpointing to notebooks. So this is from another paper where researchers have experimented with dumping the entire notebook server with CRIU, which includes the session state, to this memory dump here. And then if they want to restore the notebook server, they can just load that memory dump, and then the entire notebook server along with the session state will be restored. And one benefit this has over just naively dumping the state after every cell execution is that subsequent checkpoints made with OS-level checkpointing can actually be performed incrementally. So every new checkpoint would only store the change data after every cell execution. So this cuts down on the storage cost for storing checkpoints. But the issue with this is that the approach isn't very generalizable. So in their demo, the researchers showed the checkpointing system working on a very simple notebook in which they declared some string variables, read some files, printed some stuff, etc. on a Linux machine, which as expected, it will work there. But if we move to some more complex notebooks where, say, users load data onto GPUs or invoke some multiprocessing libraries, then this is where CRU fails. So if you try to dump a notebook session containing these things with CRU, it's just going to straight up telling you that doesn't work. Similarly, it doesn't work on other platforms, as the name suggests, like Windows or Mac. So now we basically have two methods. One is pretty generalizable but not incremental. The other is incremental but very specific to workloads. So can we actually take some big brain approach and combine the two? And then it turns out that if we do know what cell executions are doing, we can basically just manually store only the change data after every single cell execution. So given this simple cell execution here, where the user declared a new variable called CMB model, if the users know that this is the only new thing about the cell execution, they can manually save this variable using different tools like Store Magic, which is Jupyter's own wrapper around Pickle, the Pickle library itself, or other Pickle derivatives like Cloud Pickle or Dill. And it turns out there are two problems with this approach. One is that correctly saving the change data, it turns out, is actually very non-trivial. It requires some expertise. So given this very simple example here, where you have two variables, two lists, and list inner and list outer has a reference to list inner. So if you want to checkpoint and restore these two variables, which share a reference between them, naively by separately pickling them and then loading them back into the session, it turns out that you preserve the values of these variables. List outer is still a nested list, list inner is still an empty list, but you break the shared reference between them. So incorrect storage of variables can risk breaking shared references. And then similarly, correctly identifying change data also requires expertise. And some notable examples include control flows, because for example, in this very simple code snippet here, it's pretty hard to know whether the array instance was shut down without actually running the cell code. Or linking back to the previous point, you can have hidden updates in cell executions. For example, with the two lists that we described earlier, this second cell here appends a 1 to list inner, but then it turns out that it also updated list outer through the shared reference, despite list outer never even appearing in the second cell. So to sum up all these existing approaches, the first approach is to rerun cells. The benefit is that it's very convenient if you have all of your execution history on hand. And the problem is that sometimes you don't have the time for doing that. The second approach is to dump the state after every single cell execution. And the benefit is that it's notebook native. It works in most cases. And the problem is that depending on where you're doing this on, you might get yelled at by your colleagues or lab mates for hogging up all the storage space. The third approach is to use OS-level tools to checkpoint the entire notebook server. And the benefit of doing this is that checkpoints can be made incrementally. And the problem is that it doesn't work with many of the libraries that notebook users want to be using nowadays. And finally, the big brain approach of manual storage. It has the benefits of both being native and also being able to create incremental checkpoints. But the problem is actually challenging for users to perform correctly. But as it turns out, this limitation of manual storage is actually the least fundamental out of the four. So we were thinking to ourselves, can we actually build a system that somehow automates correct detection and storage for changed data? And based on this vision, we proposed a potential notebook checkpointing system that looks like this. So it's like a tag-on checkpointing system to notebook sessions where, say, the user begins with running a cell execution, which declares some variables into the state. So our checkpointing system will checkpoint that. And then suppose the user runs some more cell executions, for example, operation 2, which creates a new data frame called clean data. Then instead of dumping the entire session state, we will just store the difference between the state before and after executing the cell. In this case here, the clean data variable. And these differences are so-called state deltas. Similarly, for some more cell executions like operation 3 here, which performs feature selection and declares a bunch of new variables, we will again only checkpoint these newly declared variables or modified variables to our checkpointing system. Then, for undoing cell executions, for example, from the state after executing operation T3 to that of operation T1, we will compute the difference between these two, difference in state between these two cell executions, and then only load the data that differs between these two states to incrementally check out. And finally, suppose the user is at operation T3 and the kernel crashes, then to restore the state, we can kind of piece back together the session state from all the incremental checkpoints that we made earlier to restore the session state of T3. So the main problem that arises in all of this is that we want to define state deltas at a granularity that makes correct detection and I/O easy. So by granularity, I mean that we want to view state deltas in terms of what variables were changed or what data was, what objects were changed, and so on, for example. And one very natural candidate for granularity was just to check everything at the variable level. It's very natural for notebooks because many notebook systems present data at variable level granularity. For example, Jupyter Labs variable inspector displays our data at variable level granularity, so it shows you what's contained within each variable. Similarly, IPython's built-in store line magic stores and loads variables at the variable level granularity. But it turns out that detecting deltas and storage deltas at the variable level granularity is actually quite tricky, and it was also what caused the non-trivial problems that we had earlier. If you naively store data variable by variable, you risk breaking shared references. And also, if you detect deltas at variable level granularity, cells can potentially contain hidden updates. So we clearly wanted a granularity that was easier to work with. And our intuition for choosing such a granularity was basically based on how can we actually correctly store this pair of lists that share a reference. And it turns out that the solution is actually quite straightforward. We can basically just treat reference sharing variables as a single entity. And what I mean by that is, given this example here, instead of say separately storing or pickling the two variables, we will put them into one unified wrapper, store the wrapper instead, and then for restoration, we will load that wrapper, unpack the variables, and then by doing that, we have preserved both the value and the structure of list inner and list outer. So by treating reference sharing variables as a single entity, we preserved the shared references. And the other benefit of this approach is that it coincidentally also solves the problem of cells containing hidden updates. It makes delta detection very straightforward. So given this two cells that we saw earlier, instead of like pondering to ourselves whether the second cell updates list inner or list outer, we would just straight up say, well, it updates the entire thing. So we actually wrote a paper on this, and reference sharing variables is quite a mouthful, so we just simplified it to calling these things covariables instead. So I'll be using this term in the next few slides. So given now that we have this covariable level granularity, I'm going to talk about how our system tracks and stores these deltas. So suppose here I have a very simple example of like 3 cell executions, and then after the user runs these 3 cell executions, the state would probably look like something like this. For example, you have the variable names here, and then you have like all the different objects in the session state over here. And then the edges are basically references between objects. And these edges are found according to the Pickle protocol, or more specifically on the reduce function, which tells Pickle how to traverse the objects for serialization. And then these reference graphs also define the covariables that we'll be working with. So our system incrementally maintains these covariable tracking reference graphs through basically what is like live analysis. And this incremental part is important because object traversal turned out to be quite expensive, which I'm going to talk about in a while. And as we mentioned earlier, now it's more graphical, but covariables does enable storage like independent data tables, because you can just store covariables as like independent entities, and there is no risk of breaking shared references between covariables because there are none. And next, covariables enable very efficient delta detection, because so for example, given a fourth cell execution here, which sets object of foo equals none, we can basically trace the object graph to see that, well, object is in covariable 2. And because there are no shared references between covariable 2 and covariable 1, we can just straight up skip checking covariable 1 for updates, because we know that the user couldn't have reached anything over here by referencing. So the only question remains is that how can we systematically capture all the variable references in a cell execution? It turns out that there's another straightforward method for doing this, in that the notebook session state is essentially a dictionary. And because it's a dictionary, we can patch the getter and setter methods to capture variable accesses and assignments and such. And then if we say modify the get item and set item methods, when the user executes a cell like object.foo equals none, we can basically just check the records to see what the user actually did in a cell execution, which conveniently solves any problem with like, say, control flows and such. So given these detection results, we can now use them to incrementally maintain the covariable tracking reference graphs. So this first cell here, as we saw earlier, assigns to the variable object. So we are going to check within covariable 2 for updates. And it turns out that my class no longer has a reference to B. So the change that this cell execution incurred was that covariable 2 is no longer like one single covariable. Now we have 2 covariables, one each for list, one, and object. And this would be the state delta of this cell execution, where the covariable consisting of 2 variables was deleted and 2 singleton covariables was created. And this is what we want to incrementally checkpoint. And now that we've identified what we want to incrementally checkpoint, I'm going to briefly talk about how our system actually manages these checkpoints and performs incremental checkout. So our system manages these covariable granularity deltas in a manner that's very similar to, like, say, Git commit graphs or just like database versioning, where you have like cell executions which are timestamped, and their corresponding deltas are also timestamped. For example, in this first code snippet here, where the user declares a data frame and then declares an empty machinery model, the delta will be these 2 new variables. It's going to inherit nothing from the previous cell execution because there is none. And then in the second cell execution, where, say, the user actually fits the model, the delta will be the fitted model at timestamp T2. And then it's going to inherit the data frame from timestamp T1 because this new cell execution did not modify the data frame. Similarly, for cell T3, where the user declares a plot, the delta will be the plot, and it's going to inherit both the model and the data frame from cell T1. So suppose now the user wants to check out from the state of after executing cell T3 to that of cell T1. So the source is over here, the target is all the way up here. Then we would have to compute the difference between these 2 states. One thing that we notice is that we don't have to do anything about a data frame because they are the same object. No cell execution between these 2 states modify the data frame, so we can basically just skip doing anything about it. But we do have to update the machine learning model from that of cell T2 to that of cell T1, because cell T2 modified the model by fitting it. Then after checkout, in Git-like fashion, new cell executions will basically be stored into a separate branch, like here cell T4, which fits the GMM model with different parameters, which will create similar deltas and inheritances. And one thing that arises in all of this is that not all variables are pickable, or not all data is pickable. So our system does handle unserializable data. So for example, if we're trying to check out to, say, cell T3, and then the plot was not serialized because it contains, like, say, a generator, then we can still restore the plot variable. It turns out that we can basically look at the cell code for cell T3, plot equals GMM.result, realize that it has a dependency on the variable GMM from cell T2, load that, and then rerun the cell to restore the unserializable plot. So basically, we can restore unserializable variables by cell replay. Right, so that's enough of me blabbering. I do actually have a system demo prepared to showcase the current state of our project and what it actually does. And for that, I have a very simple data science notebook prepared. And if you're interested in trying out our system Kishu for yourself, you can also scan the QR code here or just pip install it on your laptop. So the way it works is that I'm going to start a new kernel. And we've integrated our system with Jupyter Lab in the form of this drop-down menu here, which contains a few very handy options. So the first one is to initialize our system on this notebook session, where after I click that, as I mentioned, our system will start tracking the cell executions that one performs in this notebook session. So the first few cells are very straightforward. You import packages and declare data, read data, check the data frame, and so on. And then the user, say, would proceed with, say, like creating new data frames for like text cleaning and then feature engineering and such. And while I'm doing all this, as we mentioned, our system is incrementally checkpointing state deltas to this on this database file over here. As you can see here, it's continually growing in size. So suppose after doing feature engineering, I'm going to pretend that I'm on Kaggle. I'm going to do what many Kaggle users do, which is to drop the data frame columns that they think they no longer need. In this case here, the text columns, which I think is taking up a lot of memory. So I'm going to run this cell. And you can see here that the text columns are gone. But suppose I realize that I actually need those columns for later. Then with Kishu enabled, I can basically just go to a drop-down menu, click undo execution. And then it is going to roll back the cell execution in which I drop the data frame columns. It's even going to erase the execution number to tell the user that the execution was rolled back. So we can check the data frame.head, and then we can see that the text columns are back. So we can now proceed with doing like some more stuff like train test splits, and say fitting some simple machine learning models like a multinomial classifier. So, okay, the score looks pretty good. But suppose the user wants to do more explorations in this session state, but they don't want to risk losing this like good model. Then what they can do is they can sort of like leave a waypoint with kishu.commit. I'm going to give it a name, say like checkpoint. And then what that essentially does is that it will allow users to return to this checkpoint whenever necessary, so they can now mess around with the session state, like overriding the model variable with a different model. They can look at the store, it looks horrible. Then in order to go back, suppose to their good model, they can just click Kishu checkout, check out to the previous session state, and then we can verify that the model is now the old multinomial model instead. And one thing that commit and checkout enables is that it allows users to restore the session state after a kernel crash, which I'm going to do right now. So I'm going to shut down the kernel, create a fresh kernel, and then we can verify there's absolutely nothing in this kernel. And in order to restore the session state that they just checkpointed, the users can click and initialize Kishu, and then just check out to the checkpoint that they created. And then they'll be able to see that, well, all the variables are back, including the model. All right, so that's about it for the brief demo. We showcased how our system can handle like undoing cell executions and commits and checkouts like it. Now moving on to some stuff that we are working on right now, or that we are currently exploring. The first one is object-level deduplication. So in the example that we saw earlier, where the user dropped some columns in a data frame, so the data frame itself is a covariable, and this cell execution logically updates the data frame. But not everything in the data frame was updated. Apart from the columns that were dropped, the other 3 columns here are completely the same as those in the data frame here with the tweet text columns. So instead of repeatedly storing these unchanged columns, we are currently investigating how to avoid storing within covariable unchanged data with object-level deduplication. And the second thing that we are currently working on is to develop a full-fledged GUI for our system, which I actually have pulled up here. We conveniently named it Kishu board. So what it does is that it visualizes the cell executions and all the branches that the user has created through, like, say, running cells, undos, and checkouts over here, and allow the users to directly, say, do stuff like checkout commits on this checkpoint graph, and also do other convenient things like finding which cell executions modified a certain variable and so on. All right, and going back, to conclude this talk, we built Kishu, a new incremental checkpoint and restoration system for computational notebooks. It helps users undo cell executions and version notebook states. And in order to do that, it had to address some delta detection and storage challenges, like delta granularity, how to profile deltas, and so on. All right, I think that's probably about it. Thanks for listening. So we do have Kishu here installable as a PyPy package with pip install here. There's also a QR code to our repository here in this corner. And I actually, because of time constraints, I skipped over like a lot of the technical details, but we do have like papers on these. So if you're interested, read our papers here. And I'm also happy to answer any questions or have offline discussions. Thank you. Oh, so our system actually doesn't know that. That's one current limitation of the system, is that it doesn't really track anything that happens outside the notebook session state. Like, suppose your function calls an external API or loads a file on disk. So we basically have to assume that the state outside of the notebook remains consistent when doing the cell replay.
Yeah, thank you so much for your talk. That was super interesting, and it's a really impressive system you've built. I have a love-hate relationship with Jupyter Notebooks because I love them for their convenience and I hate them for promoting a lot of bad engineering practice. And a lot of the examples you had could actually be solved with better software engineering practice, like creating checkpoints yourself and creating artifacts instead of running your entire pipeline every time you run your notebook. And then another thing about Jupyter Notebooks is that they rarely are reproducible. There's like 1% of them that are out there in the scientific world actually run from start to finish. So if a user regularly has to run their whole notebook from the top, I would consider that a good thing because it's a built-in check that your work is consistent and working. So while I totally get the sentiment of your work and I really appreciate it, what are your thoughts on how an undo functionality interacts with these concerns?
Oh, so I guess for the first point that you mentioned, we are also in the same boat. I actually developed this because I hate working with Jupyter Notebooks as an undergrad. Like, they crash so often, and I do dumb stuff in them, so I have to like undo cell executions all the time. But so for the second point, I think undoing cell executions helps you sort of like, how would I put it, like get back onto the right track. Since you can, if you run a cell and it doesn't really work, you can basically undo and then just delete that cell. So you can kind of just like keep your notebooks like exploration free. Although I don't think that's probably like a very good answer. I'll probably need to think about it more, but yeah, I don't.
Yeah, thank you. Sort of echoing some of the comments that were just made. So one thing that you can improve in terms of like using notebooks is not using JupyterLab. Using VS Code and the native integration of notebook features into VS Code have really helped into like moving into like using more regular software engineering practices. So to that end, is Kishu compatible with notebooks in VS Code or no?
I would say in principle it is. We haven't actually integrated it with platforms other than like say JupyterLab or Jupyter Notebook right now. But all of the functionalities of Kishu are basically the only dependencies is on the IPython kernel itself, which I believe many of these notebook systems actually use.
Yep. Thank you.
Hi, I have a few questions about the text side. So when you are trying to do the covariable, basically you need the relations between all the variables. And you said you can follow the reduce function, which which objects provides for pickle. What if the object itself is like, say, does not support pickle and does not have the reduce function? Are you able to follow all the tracks from objects to objects?
In that case, we just treat it as like a terminal object and just like stop it right there. And then since the covariable does contain like an object like this that's not pickable, we wouldn't really be storing it anyways. So we will be relying on like say cell replay to restore that covariable instead.
Okay, what if there is a project that supports the protocol but does not fully restore the object?
Oh, so you mean like an object being different if you like say being different if you pickle and unpickle it,
Yes.
right? We assume that objects are the same before and after pickle, so I think in that case it is actually a limitation of our system.
Okay, and another question is that you also mentioned that you need to calculate the delta based on the access to the global variables, so that basically you monkey patch the global's function to figure out the access. What if the access is actually in a locally defined function, so it does not go through the global variables?
Oh, so you mean suppose like I have a function defined and inside it I
Yes.
access like some non-primitive like list, right?
Yes.
We've tested this. The monkey patch namespace actually does pick this up.
Okay, also the things like get ATTR or some weird way to access attributes or variables?
There could be things that we have missed, but I think so. We tested it with like some of the more like interesting ones, like with statements or like intermediate variables and for loops and such. And I think up to now, I don't think we found an exception where the monkey patch namespace doesn't pick up the variable reference.
Okay, thank you very much.
Yeah, I thought that was great. I have a question about when you're once it's saved the state and stepping through the notebook, how does it interact with if someone were to go back to a previous cell and change the code but not run it, and then you try to like back into the state? Does the changing the text in the cell, is that logged as a state change that can be undone, or how does that work?
That is actually not logged. Our system would basically just undo that change you made to the cell code. But so we are currently also like investigating how to decouple like code state and variable state, so to better like say enable users to like say change code on the fly without like actually executing it for the moment.
Let's give another round of applause for Dr. Lee. Thank you very much.